Fuel specifications are the means by which producers and users of aviation fuel identify and control the properties necessary for satisfactory performance. All aviation fuels, then, have a specification number. For instance, Jet A1, the fuel normally used in jet engines, has a specification number DERD or DERD 2494. Other jet fuels have different specification numbers. Gasoline is the fuel normally used in aviation piston engines. Gasoline has a specification number DERD 2485. Contained within that blanket specification number are grades of gasoline such as Avgas 100, Avgas 100LL, and Avgas 80. Many tests are carried out on the fuel when it's manufactured. One of those tests is used to determine the octane rating. To do this, the particular blend of fuel that we are interested in is compared with two reference fuels under standardized conditions in a special test engine. The two reference fuels are called iso-octane and normal heptane. Iso-octane has very good combustion characteristics and shows little tendency to detonate when mixed with air and ignited at high temperatures. It's given a rating of 100. Normal heptane, on the other hand, detonates very readily and has a rating of 0. The particular fuel that we are interested in is compared with a blend of the two reference fuels. This is done by first running our fuel in the special test engine and then trying to produce the same degree of detonation in the engine while using a blend of the two reference fuels. If the blend of the two reference fuels which gives the same detonation characteristics is, say, 95% iso-octane and 5% normal heptane, then our fuel under test would be given an octane rating of 95. The octane rating is considered to be a measure of how well the fuel resists detonation, or its anti-knock value. Originally, tests were based on an air-fuel ratio which gave maximum detonation, but this condition is not truly representative of the working range of the engine. Maximum detonation occurs with economical mixtures which are normally used for cruising, but for takeoff and climbing, rich mixtures are used. It's important to know how the fuel will behave under these varying mixture strengths, and so aviation fuel has two ratings. This is sometimes referred to as the performance number or performance index. As an example, Avgas 100 is a 100-octane fuel with a performance number of 100/130. The lower figure is the weak mixture detonation point, and the higher figure the rich mixture detonation point. It follows that if an engine is designed to use a certain grade of fuel, then a lower grade should never be used, as this would cause detonation. If at any time the correct octane rating is not available, then a higher octane rating must be used. To increase the octane rating of a fuel, tetraethyl lead, or TEL, used to be added. For instance, 2 grams of lead were added to each gallon of fuel to take its octane rating to 115/145. The action of tetraethyl lead is to reduce the formation of peroxides, which act as fulminates to explode the end gas. But it has to be used with care, as during combustion, lead oxide is formed. Lead oxide is not volatile at these temperatures, and it has a corrosive effect on the exhaust valve, its seat, and the spark plug electrodes. To prevent this corrosion, It's necessary to add ethylene dibromide to the fuel to change the reaction during combustion to allow lead bromide to form. Lead bromide is volatile, and thus it's easily ejected as a halide with the exhaust gases. Lead in the atmosphere is absorbed into the bloodstream, especially organic forms such as lead bromide, which are fat-soluble. Because they're fat-soluble, they therefore have a particular tendency to distribute themselves into the brain and will cause damage there. Because of this obvious threat to the health of anyone who breathes in exhaust fumes, the fuel companies now use different additives in the fuel to raise its octane rating. Thus we have fuels such as Avgas 100LL, the LL standing for low lead. To make it easy to identify the fuels, they are coloured differently from each other. For instance, Avgas 100LL is coloured blue, while Avgas 100 is coloured green. Avtur, which is aviation turbine fuel, is either clear or is a straw colour. To assist in differentiating between the fuels when refuelling your aircraft, all refuelling equipment is marked in such a way as to make it easy to identify which fuel may be dispensed from a particular device. The colours of the labels on the equipment and the pipelines are shown here. Some aviation authorities do allow the use of automobile gasoline or MOGAS in some aircraft. However, within the United Kingdom, the rules governing the use of MOGAS are laid down in airworthiness notices numbers 98 and 98A. Further information on the use of MOGAS can be found in the CAA Safety Sense leaflet number 4A. Great caution should be taken when using MOGAS. It has a much higher volatility than Avgas, and consequently will evaporate much more quickly. This means that the possibility of vapour locks and carburetor icing occurring is much greater than would otherwise be if Avgas was being used. The most common contaminant in fuel is water. Water is always present in the fuel in varying amounts despite the manufacturer's stringent quality control and the preventative measures taken during storage and transfer. However, further measures can be taken to minimize water accretion once the fuel has been transferred to the aircraft tanks. Once the fuel is in the aircraft fuel tanks, the main source of water contamination comes from the atmosphere that remains within the tank. If the tanks are topped up to full, then the atmosphere is excluded, together with the moisture it contains, thus minimizing the likelihood that the fuel will be contaminated. If the fuel can be allowed to settle after replenishment, then the water droplets, being heavier than the fuel, will fall to the bottom of the tank and can then be drained off through the water drain valve. Each fuel tank is equipped with a quick drain. This is located at the lowest part of the tank, sometimes within a sump, which will collect any water as it settles. These wing tank quick drains should be used first to drain the sumps. Sufficient fuel should be allowed to flow to ensure removal of contaminants. This fuel should be collected in a suitable container, examined for contaminant, and then discarded. After draining any amount of fuel, always ensure that no fire hazard exists before starting the engine. After using each drain, always ensure that it has been closed completely and that it is not leaking. While you're in the vicinity of the fuel tank drains, you might as well check the fuel tank vents. Each tank is fitted with a forward-facing vent pipe which allows atmospheric pressure to be maintained inside. They are usually fitted in the lower surface of the wing. Make sure they're not damaged or that they're not blocked up in any way, otherwise a depression will form in the tank and will prevent the fuel getting to the engine from that tank. The fuel strainer is also equipped with a quick drain facility. The fuel strainer itself is located at the lowest point of the fuel system, usually somewhere in the engine compartment. The fuel strainer should be drained once for each of the tanks which can be selected on the aircraft's fuel selector valve. Once again, sufficient fuel should be allowed to flow to ensure complete removal of any water. A simple light aircraft fuel system is shown here. The fuel is contained in 2 wing tanks, each of which we have seen has a quick drain fitted at its lowest point. Fuel quantity is gauged by a simple float-type sensor and is shown in the cockpit on 2 separate dials. Float-type sensors are fairly unreliable, except either on the ground or in prolonged straight and level flight. So, before flight, always visually check the fuel contents by removing the tank filler caps and looking into the tanks to make your own assessment of the quantity. The fuel passes to the engine system via a tank selector valve. This allows the pilot to draw fuel from each tank in turn and thus keep the aircraft balanced laterally. Next in the line is the fuel strainer, at the lowest point in the system. Remember, the fuel strainer should be drained twice via its quick drain, once with the fuel selector valve on each tank. The electrical fuel pump is next in line. It's sometimes called the booster pump or the auxiliary pump. It's fitted to the system in case of failure of the mechanical fuel pump. The pilot's operating handbook for most light aircraft advises that the electrical fuel pump should be switched on for takeoff, flight below 1,000 feet, and for landing. It's also advisable to select this pump on when using the tank selector valve to change tanks. Notice that there is a fuel pressure gauge fitted to the instrument shown. This can be used to check the output of the electrical pump when the engine is not running. Downstream of the electrical pump is the engine-driven mechanical pump. The fuel pressure gauge will sense the output pressure of the mechanical pump whenever the electrical pump is switched off. High-wing aircraft with tanks only in the wings may not require a fuel pump, leaving gravity as the prime mover of the fuel to the engine system. The final item in the system is the carburetor. This meters the fuel to the engine through the authority of the throttle and the mixture control. The priming pump is a hand-operated device which is used to pump fuel to the inlet valve ports of the cylinders prior to engine start. The priming pump takes its fuel from the top of the fuel strainer. Great care must be taken to ensure that the priming pump plunger is locked in after use. If it inadvertently becomes unlocked, it may vibrate open. This will create a risk of fuel being sucked from the top of the fuel strainer into the inlet manifold of the engine, thereby making the mixture extremely rich and perhaps stopping the engine.